So now let's invite to a masterclass on generative adversarial networks. Generative adversarial networks, or GAN, this is one of the types of creative neural networks. They allow to create new objects. Looking at examples of these objects from the training selection, modern GAN architectures can simulate images of non-existent people. They can create some dental restorations or hadron collider. Higher School of Economy is going to be with us here today. They specialize in big data analysis and different methods of this analysis. He will tell us how to classify objects and how, with the help of GAN, we can create a non-existent human face. Additional materials on the subject during the presentation can be obtained via scanning the QR code. You will see a QR code on the screen. And Artyom, over to you now. Hello, everyone. This is a masterclass on generative adversarial networks, and it's not going to be just a presentation or just a speech. I will try to make it as interactive as possible. So I have prepared some code, and we're going to work with it together. I hope you can find a link to this code via QR code. Please scan the QR code, and you can find that code. Please scan the code now. You have the time for it right now. Please follow the link and stay with me during the presentation. Meanwhile, let me scan the code myself and go to the materials. Here is the so-called Jupyter notebook. We're using the resource that's called Google Colab. And Google Colab helps us use Python code, and it can be done on Google machines, and we can do it interactively. Briefly, agenda for today, for this presentation, my masterclass will consist of 4 parts. I was trying to make it as broad as possible with so that it's very understandable for everyone. So the first 2 parts even are devoted to just introduction. We're going to get started with the neural network. It's going to be quite concise, but I hope it's going to be enough for you to understand what is a neural network. So we're going to begin with just getting started with neural network and how components are interconnected with each other. Then the third part is an example that will show how you can classify something with neural network. And it's going to be really important for us to do something that we're going to do today. Generative adversarial networks are the networks that can draw images of people. They are used to create fakes. It's a well-known thing that is used for creation of different images online. So the third part is just an explanation of what actually generative adversarial network is. And the fourth part is where we're going to try and draw people's faces. Let's get started. Our notebook begins with import functions. I hope that my audience knows what Python is. I will not explain what Python is and how to use it. Here we just connect the libraries that we're going to use today. These are more or less standard things. I'm sure you're familiar with them. If you have never worked with neural networks, if you've never worked with them, then one of the well-known databases is TensorFlow, and another one. These are databases that are used to train neural networks and to build neural networks, and they have some functions for these purposes, and they allow you to work with the hardware that we have on hand here at our disposal. For instance, we can use hardware with accelerator, and it helps us use the resources of this hardware to the maximum. So let's begin with the first part. The first part is how can you get down to neural networks from linear models? Let's look at a simple task of supervised learning. We have a set of dots. We have them here. I put them here as this multitude of pairs. We have x and y, x1, y1, x2, y2, x and yn, etc. So the task right now, the task for the supervised learning is to predict y variable by x variable. Let's take an example of dots. I just put random dots here. Let's put them into the box. Here's the set of dots. Let's try to build a model to predict y's by x's, to predict y values by x values. We see that there is a more or less linear correlation here with some noise. Actually, I must confess that I created these dots myself, and I know the rule according to which it was created. It was just a linear law with some noise. It was kx plus b with normal noise for y. So let's try to approximate it according to the same rule. K and B, let's try to find them looking at these dots so that this rule describes the dots that we observe as accurately as possible. This rule has a few attributes. It has input x and output y, and a b parameter. We'll need to choose b parameter. And graphically, this rule can be shown this way, as this graph, this information goes left to right. So input is on the left, x and y. They are input and output. And we added also a 1 here, dot number 1. So every dot corresponds to a value, to a number. In the future, they will mean some neurons and neural network, but now they're just some values, some characters. And the lines connecting x and y, y and 1, it corresponds to the number that corresponds to this connection. And it's a sum of all connections. Y is going to equal to x multiplied by k and y multiplied by b. So our task is to choose parameters a and b in order to describe the dots that we have seen before. We're going to understand it a little bit later, but we will see that these linear interdependencies, they are components of neural networks. And it means to us that we can use these frameworks, the code that is used for neural network training, to train simple linear models, some primitive linear models. And here is an example of how we're going to do it. The cornerstone here is the main class that we're going to use. It's sequential. It's a special class, special type that we use to create models that have a set of successive steps. First, one transformation and another transformation. Here we have a linear transformation. Linear transformations are here depicted as dense. This is what we do here. Number 1 here corresponds to the number of outputs in our linear models. We see we have only one y on the right. This is why we have only one output. This is why we put 1 here. We have created a model, and a little bit in lower here there, next we have another function here, but the idea of this function is that it accepts the model and data, and it draws this data and predicts the model. If we run it now, then we will obtain this picture. The model has not been trained yet. We just created that. K and B parameters were initialized randomly, and this random initialization is in line with this black curve. The dots of our data set are here, and the red lines show errors. I mean, the difference between the dots and the line, the curve that we need to obtain. These errors need to be minimized. This is how we're going to train the model. Out of this, we come to a conclusion on how the model can be trained. In order to train the model, we need to type we need to have a loss function. We need to define the loss function for every data set, for every curve, for every line. It will give us the number that will correspond to how well the model is choosing the data. And the higher the losses are, the worse we feel. The lower the losses are, the better we feel. And we can have different loss functions here for regression right now. What's good for regression right now? When we are continuously having this value, y can be here continuously in this range. For this task, there is a typical loss function, average mean squared error. We take all these values, we increase them by the factor of 2, and then we make them average. When we minimize them, we minimize all these deviations together. If we can minimize it, then we will see some interdependence correlation with minimal error. What else I need to say here is that neural network frameworks like TensorFlow, like we're using here right now, looking at the value of a loss function or looking at the loss function at some point in the model, they can predict where we should move our parameters, where we should move our loss function to minimize losses. They do it automatically. It's not even visualized here. So just train the function, and when it's being trained, it will iteratively do these steps in somewhere inside the structure of framework. We'll look at the function, loss function, at every point in time, and framework is going to calculate towards which direction we should change the parameters. And when you repeat this step many times, step by step, successfully, you will reduce the loss ratio. And here, everything happens in this cell with code, in this box with code. First, we need to copy this function before we do the training. We need to fine-tune how exactly we're going to optimize the model. Optimizing the model is actually taking these steps when you change parameters of the model. This is training exactly. As I said, frameworks know how to know where they should go. They know how to choose the direction where to go. But there are additional peculiarities, additional features there on how to go, and there are additional optimization algorithms that use it differently. During the masterclass, we're going to use two algorithms. One of them is called RMS prop, and a little bit further, we're going to have another algorithm, alum. How they work, what's inside them, it's going to be outside of this masterclass because it's a bit too complex. But here we're going to see how we're going to optimize it, how we're going to train it, and what exactly is going to be the loss function. And on top of that, we have additional optimizer model here. Then we do training. With this function, we run the cycle. And after it's completed, we will have some visualization of loss curve, the way it was changing in course of steps. So at step 0, there was very high value. Then it was descending, going down and down. And here in the end, it's not changing, almost not changing. And if it goes down, and it means that the model, at least it has improved. It has become better than it was before. Then we repeat the code that previously we had a code for a non-regular model. Now we have a regular model. We draw this curve, and it's going to be the best thing that could be achieved here. Linear rule has been implemented here, and all other deviations cannot be described by linear rule, and they were connected with random deviations, as I said. So these errors, we will not be able to get rid of them. I hope it was clear. Now let's make it a little bit more complicated. Let's take another set of dots. I'm doing it randomly myself by hand, but here you can see that it's not a curve. If we try to train it with linear regression, we're going to get some strange thing. It's not going to work at all. I hope that this dots distribution looks like a hyperbolic curve. some cubic dependence of y on x. Let's try to make this equation then k multiplied by x plus k2 multiplied by x2. So you can see the equation on the screen, and graphically we can draw it in the following way. It looks this way. This is a visualization. We see that it's still linear. This is why this visualization still works. We can have a lot of inputs here. You can see x, x1, x2, x3, and 1. Then we combine them linearly. We multiply them by a ratio, and then we put them together, and we receive a y value. I hope you agree with what is visualized here. It's in line with this equation. I hope you get it. You can take a different look at this. Here I was visualizing it, pretending that x1, x2, x3 were not dependent on each other, but we can transform it further with another step. I decided to visualize it this way. Errors here, and here we have P1, P2, P3, which mean that we are multiplying it by the factor of m. Here a factor 1, here a factor 2, here factor 3 to the power of 3. And here we have many layers of the model. The model automatically becomes, it consists of 2 layers now, and we can implement it in our code. We use sequential model to do that. It's a sequential set of steps, but now we're going to have 2 steps. The last step is going to be linear still. It's just a linear combination of what we have here. The first step, we need to manually understand what we will need to do. We have a lambda class here, and it helps put some function here, and this function is further going to transform our data somehow. So we just type in this function here. It must be over here. It's applied over here. We're just putting together, we're like gluing together x to the power of 2x to the power of 3. We put them together here. Let me run it. No training has happened yet. It's just prediction of the model. It's going to look this way. This is the visualization. Here are our dots. And prediction of the model is the line. It's not the straight line. It's a little bit curved, which is related to the fact that these interdependence, this logic is explained by a polynomial. Now we can add more parameters, k1, k2, k3. We can choose these parameters in order to depict this data set as best as possible. We'll use another optimizer here, and we will fine-tune it differently. There are going to be more steps here for training, more training steps in order to reach good solution in the end. I prepared this material in advance. This is why I chose the values myself. But before that, there was a step of trial and error. So I made a few steps, a few iterations in order to choose the right values. But here you can see the right values exactly. But of course, you need to try and minimize the number of these errors, the number of trials in order to get the right results. You can play just with it. You can play with these parameters. For instance, these parameters defines the step, the larger or smaller step. But if the step is too large, then it might not be stable, and you will fail to find any solution. With these parameters, we can see that we get trained as well. The function was changing. And here it's almost parallel with the horizontal axis, and it's not changing. Let's see what it does to prediction.
That's the question. We see our cubic polynomial. All errors left here are related to noise. I added some dots, and we will not be able to fix those errors, but it's good that we could reproduce the trajectory. And as I said, naturally, we have a 2-layer network in part of our model. And, well, pay attention to the fact that the first step was not related to training. a dependency, so which was looking like a cubic one. So we decided to do the cubic polynomial, and this is the first transformation. We call it 3 grade. And let's imagine that in most cases this is a valid approach when we look at data and use some knowledge about them. The data could be much more complex. If we talk about graphic editing, and if we want to predict properties of pictures, it would be difficult to do it manually. Let's try the following. Let's put here a module. We'll try to train it at the same time so that we would expect that the first model would find some good transformations, and the second one would, the linear one, would form it into what we want to predict. We know just one transformation, the linear transformation, described by a class called dense, and we could graphically build it, and we could build it using 2 dense classes sequentially. But there is a problem. So if we try to create it and see it as a dependency of x from y, so again, it would be a combination of parameters. The dependency would be linear. So our more comprehensive model would anyway look like this. So x from y depends as a straight line. So a combination of linear transformation is also a linear transformation. So, and that hinders us here. We want our model to be more expressive. And actually you can fix it simply just adding a non-linear transformation here. We can make the first step, then we add a nonlinear transformations and continue. Then this law of superposition, meaning that a combination of nonlinear combinations is nonlinear because our summing transformation is also nonlinear, and as practice shown, it allows to create a model with a class with a wide range of functions it can describe. There are different non-linear functions, so here it influences on how easy it would be to train our model. So this is the non-linear function. I will not describe the way it looks like, but instead of having it as a separate step, and that's something special about our workshop. So framework creators do it that you can add this nonlinear function to a layer, and then it appears automatically there. Let me assemble the model. Let's have a look at the predictions. Here at the very beginning, it looks the model looks linear, but then we will see it's not exactly like this. I forgot to say I set 124 parameters as a number, not 3. Actually, the more dots you add, the easier it's to find a good transformation. So that's why I put a big number. Also, there is a code you probably know when you just add, well, you set the optimizing algorithms, the loss function, and we train our model. We build the training curve for this model. It takes more time, and the learning curve is more difficult in the way it behaves. It has to do with the fact that when we did that complex model, the optimization algorithm doesn't guarantee that we find the most optimal dog. It's there is a random chance. It depends on how complex the task is and how parameters were initialized. But you see that we managed to reduce error to almost zero, very low values, and again, we have something very close to cubic polynomial. We described our data very well, and our model could describe the dependencies. There is like a theorem saying that models of the type can describe any dependencies. For every function, you can find any number of that intermediate level to describe the dependency with whatever accuracy you need. So it can be really stunning. Imagine you have an image. So an image can be seen as a set of numbers, the input and the output image, and there are functions that can look at a picture, and there is a picture with a text, with a question, and it can find a picture with an answer to that question. There can be functions with skyrocketing immense number of parameters, but it's not possible that we can train the function and match parameters to find it. Actually, that's the goal for machine learning. If applied to deep learning and neural network training, the goal is to facilitate this learning track and find configurations to overcome them and fine-tune parameters of the network for it to do what we want. So here we matched model parameters to describe the dependency. However, the idea that a neural network is a function that you can match, adjust it to reproduce any function. So please have this idea on your mind. It's useful. And we use it to show an example of a classification. We will classify angles of a surface. I try to find a case. If we would draw an angle, it's normally visible. So, and normally you see its shape. We have some knowledge of geometry that allows us to do it. So if we have coordinates of 3 dots, then we would know if it is like a sharp angle, and so here you see vector A minus vector B, and that's how it's defined. If it's positive or negative, well, straight angles. Actually, we have a function that gives you, from the knowledge of geometry, let's scatter coordinates randomly, A, B, and C. And looking at this function, we would create this set of correct classifications, correct answers. So, like angle acuteness, like 0 if it's a sharper angle, and 1 if it's sharp angle, 0 if it's a blunt angle. And we take 6 coordinates, and we will get some classifications at the end. Set a data set and some examples On the left, you have blunt angles and or sharp angles and blunt angles on the right. Let's create a neural network that would be able to scatter them. Let's create a neural network and try to train it in learning this dependency on classifying angles. So creating neural networks is going on like we used before, and I added another layer. So instead of expanding, the theorem said that you can increase the width of the shapes. Well, I told you that it's possible to describe any dependency. In practice, it's easier to grow the depth, increasing the number of layers. So we increased the layers by 1, and the output is still 1, just one number. And for classification, we will interpret them. If the number is positive, then we would believe that the model predicted sharp angle. If it's 0, then it would be a blunt angle. If it's about classification, we cannot use the average, the mean square error, like in the previous case. So there is a loss theory explained in terms of theory of probability. There is a function called across entropy, and we set it here. It would expect the true mark of the class 1 or 0, and the prediction of a model from one infinity to the other. And the loss function would be minimal if the model would predict positive numbers for one class and negative for the other one. Also, I used this summarizing function tagged as summary if you want to see how your model is designed. So the functions and the numbers. We have a number of common parameters, 17,000. So it's a big number. Now, let's have a look at predictions of the model. And according to those predictions, how it classified angles by sharp and blunt, I don't see, well, the classification was not perfect because in our data set it's more probable to have sharp angles. The model doesn't know anything, so it classifies them randomly, and in both categories you have both types. Okay, let's now try to train it, so nothing new compared to our previous step. One thing, we added a strange row called a validation split. It's responsible for having the data set divided into two parts, and we will train with some optimization steps looking at just one half of data. And at the training stage, the model will not see others, and we will calculate characteristics, value of losses, and I added observation. Well, you see accuracy, the number of correct answers, and numbers we see here at the left for our training sampling is where we do the optimization steps, and additionally we look at points our model ignored at the training stage. We needed to control the so-called retraining effect. Sometimes it happens that the model begins just to follow some occasional noise. If we would go back to this case, you see that the model would twist and go between the dots. So the accuracy would still be high, but we couldn't trust into the predictions between the dots. So to do it, we see at the model's predictions on points which were not at the training sampling. We see the accuracy goes up and the loss rate goes down. You can see it graphically. You see that iteration after iteration, the yellow and red dependencies go up and the blue and green go down. Let's have a look at the predictions. Again, we take a model, see the predictions, and we sharpen the sharpened blunt angles. So here it's absolutely correct. The division, some angles, like this red one, is very close to the straight angle, but I believe that it's closer to blunt angle. And we see that the model really was trained quite well. And if we would look at properties as above, we see that the final data set of data model didn't see, the accuracy is 98.8%, so just 1% where it makes mistake. Probably in cases when angles are like this one. So, and the scalar sum would probably be close to 0, and it's not clear if it's above or below 0. So now we are finishing with that overview of neural network. For us, it's essential to have on our mind an idea that a neural network is a class of functions that we can adjust and fine-tune, and it's helpful to have an idea on how neural networks do the classification. So it's type of an architecture where you have a prediction at the end and you have a loss function that tells us in what direction we have to change parameters of the model to make it correct. So now then our next part on generative adversarial nets. It's part of creative networks that can reproduce and produce some objects. How can it be done? There can be a number of approaches. One of them that used in GAN, I will use the abbreviation not to say generative adversarial networks. Well, GAN for short. I will use the word GAN. It would be easier for me. So GANs use that approach to create objects. Just imagine a neural network with a fixed set of parameters. Let's imagine that we want to generate a picture. Then we had a number of outputs for the network corresponding to the number of pixels on the image. So one would show brightness in a certain pixel. So the outputs would be interpreted as pictures. What's for output? So a neural network is something predetermined. It has a number of parameters, and it transforms inputs into an output in a predetermined way, into a picture, in our case. To train a network to generate a number of images, we can take and supply occasional noise.
And in every number, we will randomly choose out of normal distribution, for instance. So we can imagine that we can toss a coin, and the coin generates a random number. And then the coin has a multitude of different edges and sides, and it can generate a lot of numbers. And with the help of neural network, you can transform it into a meaningful image in the end. As I said, neural networks can approximate any correlation. It means that we can imagine this correlation. It's a set of random numbers. It can correlate them into an image of a cat or an image of a human face or something. That means that there is some function that is put there and that is finding this correlation. And neural networks with certain parameters will implement this function. It will take noise in the input and it will generate image in the output. And it's not clear how to get it in practice. For instance, here it's not clear how to train the neural network, how to obtain this image, how to train the neural network so that we can get it in the end. So the question is, what is the function of losses? Which means that we need to predict the output of the model, whether it's close to images that we have. And GANs use a great thing for it. They're saying, let's add another classifier. Why don't we add another classifier? There is an object that our neural network creates, and there is another object, like a set of images that we feed there. We want to learn to predict. We want to train our neural network to generate something similar to our set of images that we upload into it. Let's add a new network that will do classification. It will try to tell apart real pictures from generated pictures, from artificial pictures. It's clear that if this network is failing to solve the task of classification properly, then it might mean that our model is not good enough, that it's not deep enough. But if our network is deep enough, if it's quality enough, it has a lot of layers and width, then poor classification in the output will mean that the set of data that had been generated are very similar to the initial set of data, to the artificial picture. It's difficult to tell them apart. In this case, the loss function in the generator will be just a classifier loss function with that is negative. So we can adjust this model in such a way so that it resolves the task here. And this is what this approach is based on. These networks have their names. What generates the image is called generator, and the classifier is called discriminator. So the main idea behind it is that we try to teach discriminator to tell to tell the difference between pictures, and a generator is going to try and prevent discriminator from doing so. Loss function of discriminator minus loss function of generator, for instance. So this is the main idea here. There are two competing pieces here. This network is trying to resolve classification, to do classify, and this network is trying to prevent the second one from classifying. If this one is doing it very well, then in the end, the objects that it generates might be similar to this data, and this is why discriminator will fail to tell the difference between them, and ultimately we will get this poor value. This was a theory introduction. Now let's get down to practice. There are some codes here to retrieve the pictures. We'll try to use GANs to create human face images. And in the beginning, we'll take some data set, meaning a set of images with human faces. It uploads pictures from internet and shows us how to do it, and it takes a few seconds to do so. While it's busy doing so, while it's busy downloading pictures, let's go to the next box. And next box is just a function that will select the set of faces, and it will draw them next to each other like a matrix, in the shape of matrix. So we will see the result here. We will see the visualization. So Okay, we see a matrix of images. We see only 25, but in reality, there are 13,000 of them there. So it's a large data set, a set of images, and we're going to implement the GANs scheme on them. Let's think how we can do it from the standpoint of modals. We already know there are some sequential models when we have a set of actions. But since here we have a complex structure, we have two paths of implementation, we will not be able to use sequential. It's not going to be enough. We will need to use generator and discriminator. They will be described with sequential, both generator and discriminator. But for the whole model, we will need to have a more specific behavior description. For this purpose, we are taking, I will scroll it down a little bit now. This is why we take overall class of models in Keras model. We use it and then we clarify its behavior a little bit. Now let's speak about clarifications. We have a constructor. It's init function where we're creating the model here. When creating the model, we're creating the networks of generator and networks of discriminator. There is another layer, reshape layer. It just takes the data and it doesn't do anything to them. It doesn't do anything to values. It just says that this data must be viewed a different way. When I said that we have a set of numbers and we reshape it into a picture, this is what the reshape function does to it. It takes numbers and reshapes these numbers into an image. It says that actually these numbers have horizontal width and height. Then there's another dimension here that there are three colors, red, blue, and one other color. In the end, we have this picture, and we need to turn it back into one-dimensional set of numbers. But actually, it's not the most difficult part. The most difficult part here is that we're doing this trick. On top of creating a generator and discriminator, we call them frozen copies, frozen generator and frozen discriminator. We create copies of them and we make them non-trainable. We freeze them. Why do we freeze them? Why do we freeze copies of generator and discriminator? The loss function, as I said, consists of two parts, loss function of discriminator and loss function of generator. And it is actually discriminator loss function that is negative with minus. When we train discriminator with its loss function, it's important to make sure that it doesn't train generator. When we connect the parameters that are responsible for discriminator loss, it's important to make sure that only discriminator parameters are here. And the only way to make sure that it happens this way is to calculate it in the following way. Here we have a frozen copy of generator that is unchangeable, and here we have a real training discriminator. And when we optimize parameters of generator, it's important to make sure that we freeze discriminator, because loss ratio of discriminator, it deteriorates the results of discriminator. We don't want them to get mixed together. We want to train them separately. So when we calculate loss functions of generator, we freeze discriminator. This is a small complication, and I hope it's clear to you. We create another function separately to generate a set of images with a generator, and here we have a parameter that helps us choose whether we use a frozen one or not frozen one. If frozen, then this one. If not frozen, then this one in the bottom. And then we choose the generator with some random distribution. There is one more trick. Since we have pairs of models, a generator and this frozen copy, and generator and discriminator and this frozen copy, after every step, we will need to copy the regular values into the frozen model. So we need to upgrade the frozen model at every step. It must be trained as well in this way. This is why we copy it here. And finally, the most important function is the call function. Call function is going to be iteratively called during model training, and here it must count all the loss functions. In order to do that, we create a set. So we use this generate images function in order to create a set of images generated by the generator. We have a set of non-frozen, and we have a frozen and unfrozen set. Then, since the generator is classifying, then we need to give it, we need to supply it with a set of right answers, with a set of truths. One is going to correspond to the true images from the real data set, and 0 is going to correspond to images that had been generated by the machine. So we just take a loss function and we call it. So we give the right answers here, and next to it we give the predictions of the discriminator for the corresponding images. In 0, images generated by the frozen generator, so that the generator doesn't get adjusted from this loss function. And for ones, we feed discriminator responses to real images, and then we calculate average from both functions. For generator, as I said, for generator, we can take the same loss function, but with a minus, negative. There's another trick that works better here. When we train the generator, we can pretend that the generated images are images corresponding to 1, with 1 labels. When we look at prediction of discriminator, actually this is a discriminator prediction, and then we put it into a loss function. We substitute them, substitute zeros and ones in the right answer. So this loss function is going to change parameters of our models in such a way that the discriminator output will give us classification for 1 class, 1 label, and but we here have generated images here. Since the discriminator is frozen here, then it will not depend on this loss function, meaning it will not get adjusted from, in this case. And this set of images, the generated set of images, it will depend on the training generator. So this loss function depends on parameters of training generator. This is why optimization is going to train the generator. Ultimately, we need to bring our losses into one function, and here we have a weighted function, weighted sum. We take these two with some weight, we add some weight here, and we add here generate a loss function. We have 2 more calls here, add matrices. It's a simplification to monitor the values at every step of optimization. What we see here, it's going to be on the screen, and we can see what the loss matrix in discriminator and in generator equals to. Both what they equal to. Let's run it. Here's an optimizer. Loss function is the same as that for classification in the previous example. We are familiar with it. Here we need to put GAN. We need to put data for GAN so that it collects all the layers together at this point in time. And here we have a summary of our model. Here we can see how many parameters we have overall. For instance, generator has 260,000 parameters. For discriminator, it has 500,000 parameters almost. We also have here 2 more generator and discriminator. These are the frozen copies. These parameters are not frozen, and we can see it here. So we have a set of non-trainable parameters and trainable parameters. One more technical thing. During the training, most probably we will want to see the pictures in the middle of the process. And here it can be done with the help of this class. It's called class callback. We just let it know that we have this class. During training, it will do this function, and the training algorithm will once in a while call this function. Within this function, we will be able to plot what we have, to plot the result. So we're ready. We're ready to do the training. Let's run it. This training is quite slow. Here we're trying to do 100 iterations, and they're called epochs. Let's wait at least for 5 epochs to run. We have done it in such a way that 5 epochs, every 5 epochs, once every 5 epochs, it draws the image. So it creates these faces full of noise. I can say that these are faces, yes, but there's a lot of noise on them. Once every 5 epochs. For about 5 minutes, we have been training the model. I stopped it prematurely because I see that the pictures are poor quality. At least they are poor for the model architecture that we are using here. Let's see what we have here. Let's run the same function, but improve the scale. Let's zoom it in. I can see that this is similar to people, a lot of noise, they're blurred. But at least we can tell these are people. And the architecture that we're using, maybe this is the best of what we can achieve, plus more or less. We can fine-tune it a little bit or play with it so that it gets a little bit better, but not much better. It doesn't have any additional knowledge on what the image looks like, so we use very general neural network architecture. And this is actually the difference between this model and other models that are state-of-the-art, that are generating something really realistic. The state-of-the-art models have the architecture that gets adjusted to images of people, for instance. It goes a little bit beyond, it's out of the scope of this masterclass. So I will not elaborate on that. There's a fragment of code that shows curves, training curves, depending on our loss function and epochs. We see that at some point they were getting trained and they got saturated, and then the generator loss goes up and the discriminated loss goes down. It means that the training system with 2 competing neural networks is not stable. It might happen so that one neural network beats the other one, and if we wait for too long, then most probably discriminator learned to tell apart the generated and real pictures, and generative function goes up correspondingly, and the quality of predictions is also getting poor. And one more research area is how to improve the quality of these methodology, how to make sure that 2 neural networks work fine with each other. It's a more complex science, but basically this is what it's about, how to train these models together. It brings me to the end of my masterclass. I have shown all that I wanted to show, and in the end, I'm just giving you a list of links on models with GAN. The first link, maybe you have seen this link, is the website that you update and it generates a human face every time. Let me show you once. It draws a person. It's a non-existent person. This person doesn't exist. This picture was drawn by a neural network. I think it's just incredible quality. If people showed me this picture and they wouldn't tell me that it was generated by network, I would really think that it was a real person. There are just very few artifacts here that prove that this is actually an image generated by a neural network. But as I said, studies that help reach this quality, they help us see how we can change the architecture, how we can step away from what is written over here. It helps us see how we can transform these data, what transformations we can do here to help the software create real images of people, most realistic images of people, not real people. And 2 more links here. They're very interesting. The second link The second link helps us draw a cat by hand, and it will try to, it will make it realistic. Sometimes images are quite creepy in the end, but it's worth trying. Some links improve resolutions of images, and it helps you launch old games and HD quality. There's an article about how GAN can be used to help generate dental restorations. Usually it's very time-consuming, and it's done by people. People are they're copying human teeth, real human teeth, and then doing dental restorations. And the last line corresponds to what I do. This is what I do at my university. We're simulating detectors of physical particles. Physics of particles. So this is a link to my work. I did it together with my co-authors, and here is one more link. It has a few dozens of applications in this area. These models are just very popular. Thank you very much, and thank you for your attention. I hope it was interesting.
Artem, a wonderful masterclass, a host of useful information. Good luck with your further developments.